going to start off with Chapter 12, three-dimensional coordinate system is where Chapter 12 starts. It's very analogous to the two-dimensional, except my pen doesn't work. You've got an XY axis, and so you got a point x comma y. Well, when you go to a three dimension, if we leave, this actually won't be how we leave it, but how would we add a third dimension to that? Well, it's got to come outward, and that's hard to do on a flat surface. But the way they'll do it is designate that axis that comes out, kind of at an angle it like that, and that'll be our z-axis, of course. But that's actually not how the preferred orientation is. The way they'll typically, I don't know about other books, but this book prefers, they'll call this the z-axis, and then the x and the y-axis will be the flat surface, yeah. Kind of like the floor. If you think about the corner of a room, that's your z-axis going up, and then the x-axis this is your floor. So that's the x-y axis is kind of the floor, and of course you have above and below the floor, but this is like the left wall, the plane. The zy plane is the right wall, and the xz plane is the left wall, if you look in that corner. But of course they extend both ways. And so you kind of have to get your mind to think in three dimensions. A little tougher, because it's harder to draw stuff, for me anyway, in three dimensions. Also, two dimensions, since we've got a real number line and a real number line kind of crossed together, sometimes this is referred to as the real numbers times the real numbers, R2. Whereas when we go to three dimensions, of course we've now got three number lines at play here, and so they'll refer to that in the book as R3. How do we name points then? Well, x, y, and z. So you need an x, come out an x, and then go over so many for a y, and then up or down for a z. And so, yeah, a point in three dimensions is x, y, z. As far as positive axis, you know that the x-axis, the positive x-axis runs this way. The positive y-axis, of course, and the z-axis are the ones we're familiar with. Up for the z-axis and to the right. All right, let's see. So have you done much with three dimensions? A little bit? It just takes a little bit of visualization, of course, and sometimes you have to think a little harder than you do for a two-dimensional situation. Now, when you go to equations, that's when the fun really begins. Let's think about the equation z equals 3 in the three dimensions R3. Of course, that's specifying the z value is always 3. No matter what the x and the y are, the z value is always 3. So, of course, just like in two dimensions, when we have like x equals 3, that sets up a number line, a vertical line, right? Because x is always 3. That means all those points, the y value is whatever you need it to be there. So you get a vertical line. Well, z equals 3. They do kind of all line up, except now we've got 3 dimensions. And so if you think about, here's z equals 3, and so all those points that are z equals 3, it would be a plane, that's right. And this is again where you have to kind of use your imagination, but it's that plane that's at the level z equals 3. So an equation like that is going to be a plane. X equals, if it was x equals 1, well, it's going to be a plane. And sometimes the way they want you to describe it in words, this plane would be parallel to the xy plane, right? This plane right here, it's just up 3 units. You know, if you did a y equals, then that's going to be parallel to the xz plane. So you just kind of have to draw it the best you can. Of course, the book can do a little better job with the graphics and so forth. So we'll rely on them a little bit. This is an interesting one too. X squared plus y squared equals 9. In R3, hopefully we know in R2 what it is, and that's actually kind of where you start. Matter of fact, in 2 dimensions, that's a circle. And so if we if you think about it here, in 2-dimensional, that's a circle with radius 3. When we go to 3 dimensions, though, you know, in the 2-dimensional case, that would be the xy plane. We're talking about a circle here. That's, you know, tilted on. Yeah, you know what I mean. Okay, but that's only part of it, right? Because that's when we have z equals 0. That's when it would be at that level on the xy plane. If we move to z equals 1, then we've got another layer to it there. It's a circle at level 1 and then a circle at level 2, and so you just keep building there, and you can kind of see here that that's just going to be this, right? Yeah, a pole. Or in mathematical terms, a cylinder that extends infinitely, both directions there. Yeah, you're just going to get a cylinder, an infinitely long cylinder, right? So that, you know, for things like that, you know, just extends things out. Instead of 2 dimensions, now we can go 3 dimensions, which makes it more interesting, I guess. While we're on it there, if we go ahead and add the z squared in with that, well, that's another story, because now we've got all 3 variables in the equation. So what it amounts to, and we can go through, you know, the distance formula and that sort of thing to get this, but what that amounts to is the 3-dimensional equivalent of a circle, which would be a sphere. Yeah, so that's going to be a sphere centered up at 0, 0, 0. And then, of course, that's going to be our radius. Square root of that is the radius, similar to in 2 dimensions, the circle. Yeah, so we get a sphere, which, like I said, those get harder and harder, tougher to draw. Of course, you got the circle all the way around, so it's a sphere. Yeah. put too much on it, it gets. But those are all the points that are that fixed distance from the center here. Those are all 3 units away from things. All right. And then, of course, if we shifted and all that good stuff, we can do the same thing. They have you play around with some of these. If we do x minus h squared plus y minus k squared plus z minus l squared equals r squared. What do you think that is? Whoops. That's just shifted, right? Yeah, that's just shifted the sphere. Instead of 0, 0, 0, now we shifted it h units, k units, and l units respectively in those directions. Translated, yes. We've translated that, so that's a sphere centered up at h, k, and l. And the radius is r. So what have we got here? What's the equation of the sphere, center 3, 4, negative 2 that goes through negative 4, 6, and 5? What would that equation be? Well, you need to know 2 things, right? Just like in a circle, you need to know the center and the radius. In a sphere, you need to know the center and the radius. Well, we've got the center, we just don't know the radius. So just like we've had these problems similar before, we can substitute. That's h, k, and l, right? And so it's x minus 3 squared plus y minus 4 squared plus z plus 2 squared. And then to find out the r, we can use these, right? Yeah, substitute those. Yeah, same thing. And a lot of times that's what we're going to do. We're just extending the 2-dimensional into the 3 dimensions, and it's very much analogous in a lot of ways. So yeah, if we plug in the x, the y, and the z, we can figure out the r squared. Was that 49? At 4, 49, 102, yeah. So the radius is the square root of that, but actually, yeah. So actually we need that, don't we? So that's our equation. All right, so lots of analogies here.